Great. Good morning, everyone. Thank you all for being here. I know this is the last day. Maybe people are tired. How's the energy right now? Are you all still feeling good? Okay, awesome. Great. So I will be talking about squeezing intelligence into the ear, a practical deployment of AI speech enhancement in hearing aids. Before I get started, I'm just going to introduce Femto AI a little bit. So hopefully the video works. There we go. We are really proud of this animation. So Femto AI, we were founded in 2018. We used to be called FemtoSense up until last Thursday. So if you've not heard this name before, don't worry, it's new. And so what we do is we're all about empowering intelligence in everyday devices. That means bringing this AI accelerated chip into really small edge applications. And a bit about me. So my name is Pong. I'm the Director of Strategy and Chief of Staff at Femto AI. I'm actually substituting for our senior deep learning engineer, Raphael, who could not join us at the conference this week. And you may notice, Raphael, he's very technical. You look at me, I'm not technical. So you're welcome to ask any of the questions afterwards. I can forward it to the engineers if I cannot answer them. All right, so now let's get into the talk. Hearing aids. According to WHO, it turns out that 17% of people who could benefit from hearing aids don't actually end up using them. I'm looking around and I see a lot of people with glasses. Now imagine if 17% of people who can use glasses don't use glasses. A lot of people won't be able to see. With hearing aids, a lot of people aren't able to hear clearly. And we wonder, why is that? The top reason for that is that people realize that there are poor benefits from hearing aids. Even if you wear them, it doesn't actually help with your hearing. And a second reason that people stop using hearing aids is that they don't perform well in noisy situations. I have a little demo downstairs that can demonstrate what this means. But essentially, what happens with hearing aids now is that there's a microphone, it takes a signal, it does maybe some filtering, and then it boosts everything. So noise is amplified, your speech is amplified, everything's amplified. So how can we solve it? Well, we're an AI conference, so let's throw some deep learning at it. Great, problem solved. So deep learning, it can separate the speech from noise. Check. Deep learning, it can also preserve speech quality. Check. And then one of the biggest problems with hearing aids right now is if you have a sharp impulse, let's say cutlery, for example, when you're out having dinner, it's like super high frequency, super high amplitude, and it's really, really painful. So deep learning, great. You can also detect for that and then solve that. And in fact, you can experience this sort of deep learning approach to noise reduction in Google Meets, Zoom, Teams right now. All right, so thank you for attending my talk. We're done. We solved the problem. Goodbye. No, we're actually at the Edge AI talk. We're about connecting AI to the real world. So let's think about deployment. OK, let's strap a GPU onto a hearing aid. OK, could that work? Maybe not. Because right now we see that, with power of typical noise reduction algorithms, it takes about 1 to 10 watts. For latency, if you're doing something like Google Meets call, you have the latency budget. It doesn't matter if you're hearing real time or not. 50 milliseconds is totally fine. And the size, I won't go into details, but it's big. So in a hearing aid deployment, power, we want to make sure that it actually lasts in a hearing aid form factor for a whole day. So 20 hours, assuming you sleep for at least 4 hours a day. And in a hearing aid size battery, that translates to about 1 milliwatt of power that can be allocated to the AI part. For latency, you want to make sure it's perceived as real time. So that translates to about less than 10 milliseconds of latency. And then for a size, to fit in the form factor, it has to be tiny. So we have a solution. We call it the Clara AI speech enhancement, and this is the flow. Once again, I want to remind you that I am not a technical person, so I will just read my notes here of what the components mean. So we start on the top left-hand side with a noisy audio input coming from the microphone. And then we bring it into our chip, the SPU001, and we do a Fourier transform on this to turn from the time domain to frequency domain. Followed by that, we do a log-mel transform and that basically puts the signal into like frequency bins, and that kind of maps to what the human hearing experience is like. Then we do some gain invariance, like the delta MFE, just to make sure that, okay, it's gain invariant. Here comes the fun part. Then we feed it into a DNN. I will go into more details later. After that, DNN predicts a mask that can be used to, multiply like with the signal to then generate this enhanced STFT that has the speech but does not have the noise. And then we inject that back to the top signal flow. I realize I have a laser. Ta-da! And then here we can do some remixing where if you want to preserve some of the original noisy signal, just for to make it sound natural, you can maybe inject maybe 20% of this, and then you have the rest, 80%, be this cleaned up signal, and finally have your clean output. So earlier I mentioned the DNN part. Let's dig a little bit deeper into that. Oh yeah, before I get into that, in addition to all this wonderful stuff I just talked about, we can also add a lot of other signal processing to this as well. One of the fun ones is the wide dynamic range compression, which is really helpful in hearing aids. But okay, back to the DNN. What is in here? We have a 40-layer temporal convolutional recurrent neural network. So the temporal convolution part is just a sliding window over time. And then, the recurrent neural network, it is able to do the wonderful predictions. I don't know anything further than that, not a technical person. All right, so how are we able to fit that 40-layer network onto a chip? So at Femto.ai, we're all about using the technique called sparsity. It was inspired by neuromorphic research that the founders did at Stanford University, but then pivoted over to purely digital design. So a bit about sparsity. I think a lot of people in the audience probably knows about it more than I do, but I'm just going to do a high-level overview. So neural networks is just a bunch of matrix operations, mostly multiplication. It turns out that in these matrices, there are some values that have really low magnitude, so they're really close to 0. And if you prune them down to 0, it doesn't really affect the accuracy of the model significantly. So let's say we go ahead and prune it down to 0. If you multiply anything by 0, it's 0. And so conventional approaches might just do the operation anyway. But what we have with our chip is custom instruction set that once it detects the 0 in the unstructured sparsity, we're able to skip the calculations. And so the result of that, let's say we do 90% pruning, then we're able to save the memory footprint by 10x, and then the power consumption actually by 100x, because if we have dual sparsity of both the weights and the activations, it multiplies. And it looks great in theory. And it's also reality. So we have this tiny little chip called the SPU001, which I'm going to hold right here. But I don't know if you're able to see it because it is absolutely tiny. You can also just, okay, I see you're all squinting your eyes at this. That's a tweezer. Those are fingers. Small. It is about 3.5 millimeters squared. And in it, we say it has 10 megabytes of effective memory. So what does effective mean here? So it has 1 megabyte of raw SRAM. And then let's say if you do, 90% pruning, then you can fit, in theory, a 10 megabyte model in the 1 megabyte footprint. And then in terms of efficiency, running the algorithm I showed you earlier, we're talking about the microwatt scale, maybe up to 1.2 milliwatts. So let's see, going back to the earlier part about noise reduction, okay, the experience of the hearing aid user, they care about these 3 main things. And then for deployment, these are the things that are the constraints that we have to work with. Going into this first part, we have a few results. So on the y-axis here, we have, let's say, the signal to noise ratio, where the higher the number, the more signal, let's say clean speech there is to the noise that we don't want to that we want to suppress. The blue line is the enhanced signal, whereas the orange line down here is the noisy signal. So what is SISDR? It is a scale invariant signal to distortion ratio. The higher the score here, it means that it is a clearer signal. So you see that across different SNRs, once we enhance it, no surprise, it has greater signal to noise ratio. Not signal to noise ratio, great clearer signal. The next metric that we have here is what's called the Haskell metric. So it's a really common metric in the hearing aid development. It stands for the Hearing Aid Speech Quality Index. So the higher the number, the greater the speech quality. So great, we're able to have clearer signal, greater speech quality. And then finally, the last part, after all, if you're wearing hearing aids, how does it actually feel? So here we have some metrics about the actual experience that users have. And no surprise here, when we enhance the signal, it's a better experience. So, all of these things are now we're able to do. And I'm moving on to the deployment part. So over here in my hands, I have a hearing aid with the chips actually in here, and then also the algorithm running on it. And running the algorithm AI for the whole time, the battery is able to last for 20 hours. The latency that's in here, for the algorithm itself, it's about, I think, 8 milliseconds. And so overall, the signal from input coming in to hearing, it's about less than 10 milliseconds. And then finally, the chip is in here, it's working, it does fit in the form factor. Nope. All right, so checked all the boxes. And I just want to talk a little bit about this hearing aid. So it's made by a company called New Sound, based in China. And they launched it early this year in March at the AAA conference. It's the American Audiology Association, if I remember correctly. And there were a lot of audiologists who came to try this out. And this is a part where I think is pretty interesting. They walked around the show floor, they tried out different AI hearing aids, and then they came to our booth, tried this. And then one of the quotes that they said was, I walked around, tried a bunch of AI hearing aids, I thought AI was a buzzword. Then I tried this, and they're like, oh, okay, now I finally hear the difference. So with that, I actually want to invite you to come to a demo table downstairs and actually hear this. Another thing I want to note about New Sound is that they got in touch with us a few months ago, and then they were like, all right, okay, we're interested in your chip, let's try it out, let's build it in. And then they were able to just build everything in 3 months, and we're like, whoa, okay, that's pretty fast. Because if you're familiar with hardware development cycles, it can be really long. So huge kudos to our friends at New Sound. There's going to be a lot more hearing aids with our chips builder coming soon, so there's a little sales pitch. Yeah, it'll be fun. And also other devices, too. All right, and with that comes to the end of the presentation. Thank you for being here. Thank you for listening. I just want to share a few other things. So, please come try out the demo at our demo table. If you know someone who uses hearing aids or who could benefit from a hearing aid, let me know. We can put you in touch to get one of these, or maybe any other hearing aids and share more. If you're interested in deploying your own algorithms onto a chip, we do have a developer portal that you can go in and then try that. And then finally, next week, my colleague John will be giving a talk in Geneva at the AI for Good Global Summit, where he'll be actually talking about the hearing aid and how edge AI can actually help more people benefit from this technology. So thank you, and now open for questions.